The exam for my elementary themes of analysis course was pushed until Monday of next week, which gives me a few days to go over the homework problems that we were given that we have to, write up the proof on during the exam. But we also have to prove one of the theorems from the past 2 weeks in the class, and unfortunately, I was kind of hoping that it would be easy for the next couple days because we didn't really cover that many theorems, but the theorems that we did cover were just super long and complicated. In my opinion, they were complicated, and it just gives me a headache going over them. And I'm gonna have to know every single one of those proofs in full detail, no details missing, in order to get all of the credit, because he's not gonna give any partial credit for it. So kind of feels bad right now, man, but I mean, I guess that's the life I signed up for. So in this video, I thought what I would do is go through at least some of this material that I'm going to study for this exam. The homework problems that I'm going to do, there's only 2 of them I'm going to do. So, and they're pretty simple standard proofs in my opinion. They're not too crazy. But the theorems are the thing I'm going to spend the majority of my time going over, because I'm afraid that I know I'm not going to be able to remember all of them, and I'm just going to have to pull a couple all-nighters, in my opinion. Probably not true all-nighters, but I'm going to spend a lot of time studying those theorems, which I'm not thrilled about. But anyway, let's go over the problems that I'm going to write up on the test, because remember, he gives us the homework problems, and then on the exam, we pick 2 of them to prove to him, and depending on what quality problem it is, will determine how many points you get. So these 2 problems were like in the middle, like they were medium difficulty, so I get a certain number of points for it. Like this problem, for example, is worth 4 points. I need to get 14. This is 4. This one is 5, so that's 9. And then the theorem is worth 5 itself, so that will get me 14 exactly. I could do harder problems and get more points that way, but I mean, he doesn't give partial credit, and those harder problems are, much harder and much more easy to make a mistake. So it's easier for me just to do these 2 medium problems and then the theorem. Anyway, so let's just go through the problem. You have this non-negative continuously differentiable function defined on the positive real numbers. You assume its integral is finite. You assume that the absolute value of its derivative integral is finite. And we want to prove that this series converges. So this is f evaluated at n for positive integers n greater than or equal to 1. So my original strategy for this, in my opinion, I thought it was kind of smart, but ultimately not really, because it didn't work. It wasn't a totally stupid idea in my opinion, but I showed it to a friend. He has a master's degree in math. He thought it was kind of clever, but ultimately there was a problem at the very end that did concern me. I was like, I'm not sure I can show that. It turns out I couldn't. But I posted it to Stack Exchange. I showed my idea. Even the guy that answered the question, which his answer more or less looked like this, he said that my idea wasn't too bad, so I'm going to take my W for what it's worth. Half W. Lowercase w, how about that? Not a capital W. And also my friend was able to solve this, and he explained it to me, so kudos to my friend for being better at math than me. So the idea is that you have this term fn in the series, and you want to compare it with the average value of the function over the interval from n to n plus 1. So that's what we have written on the left side. And then you can push the fn inside the integral. Everything there is honest. And we know from the fundamental theorem of calculus that the stuff that's in the brackets can be written as the following integral. We know that f prime exists. And then we are going to change the order of integration a little bit. It doesn't really matter that we do this step, I don't think, but we do it anyway. So instead of integrating from x to n, we integrate from n to x and put a negative on the outside, which is fine. And now what you want to do is swap dy and dx. In measure theory, we would call it like Fubini's theorem or something like that. But in Calc 3, all we're really saying is this picture. We know that x is between n and n plus 1 because of what we said right here. And we know that y is between n and x. So n is the lower bound, so we have this horizontal line here. And y equals x is the upper bound, so we have the graph y equal x, which means that our domain of integration, dy dx, is this shaded blue triangle. I shaded in the wrong triangle, but it's this blue one that we have here. And if you swap the order of integration, meaning that we do dx first, then dy, then we can see that x is bounded between y and n plus 1. If you just look at the picture this way, we have y on the bottom, n plus 1 on the top. And again, this time y is going to be between n and n plus 1. So everything's happening in that square. So we have this, which means f prime of y is independent of x. So this can pop out and go over here, which is exactly what I have. And then if you integrate 1 with respect to x from y to n plus 1, that's pretty easy to do. We end up with this. So what have we shown? We have shown that this is equal to this. And if we add this to both sides, this will cancel. So we end up with Fn is equal to the thing we added minus the thing that we got here. Okay, now we need an upper bound. So if we just repeat, or if we just rewrite this expression down here, that's absolutely fine. We still get less than equal to. But if we be greedy here and take the absolute value and just add it over, so we're just being greedy here. We're just adding this thing in absolute value, apply triangle inequality. We can push the absolute value inside. We see that we get absolute value f prime, and then what's this thing in the bracket bounded above by? It's going to be bounded above by 1. Because remember, y is between n and n plus 1. So what's in the bracket here has to be at most 1. If you just, plug in some values, you can, or even graph it if you want. You'll see it's bounded above by 1. So we get this. And these guys are pretty nice, because now if you sum up over all Fn, like we have here, the sum over all n here, which is what I've written here, sum over n here, written here, this precisely gives you the integral of f. Well, from here it's 1 to infinity, but you can be even more greedy and start at 0. You just make the domain of integration larger. Everything here is non-negative, so we don't have to worry about negative values ruining things. This gives me this integral, this gives me this integral, or at least an upper bound by these two guys. And these guys were both assumed to be finite. That was one of the assumptions, which means that this sum has to be finite, and the problem is proven. Overall, I do like this problem, but I was kind of disappointed in myself that I didn't get it as soon as I wanted. But at least I understand the theory behind it, and I can apply it later. Hold on. This needs to be somewhere else. That's from the measure theory review. Okay, so now we have the fifth problem. So this problem is actually worth more points, but it's actually a shorter proof. We're going to assume that xn is a non-negative, or actually a strictly positive sequence. Xn is positive for every integer n, positive integer. And we want to prove that the following sum is less than or equal to 1. So I'll let you read it there. It kind of feels right when you read it, because that e to negative x1 to negative xn is going to, it feels like it should dominate xn, but we have to prove it in the sense that, the sum won't get too large. So the proof is by induction. We consider the case where n is equal to 1, so we have x1 e to negative x1. We're looking at the partial sums, by the way. So we have x1 e to negative x1. We can push the e to negative x1 to the bottom. If we write this out as a Taylor series expansion, which I should have written x1 squared here, but I did not. But the idea is that everything down here is non-negative. So to make the fraction bigger, you make the denominator smaller. And I'm going to keep x1, so they end up with this guy, and that is equal to 1. So we know for sure that this claim holds for the base case. So if n is equal to 1, we'll have something bounded above by 1. So suppose I've never said that before. Suppose that it's true for n minus 1 terms, and we want to prove it for the nth term. So now we have this sum from k equal 1 to n, and in the very end we want to send n toward infinity. So we have this sum. We can peel off the first term, so we have x1 times e to the negative x1, which leaves us with a sum from k equal 2 up to n. So notice that e to the negative x1 appears in every single term of this series, because remember, this was hard for me to see, is that see here, when we start with k equal 1, this x1 appears every single time. So when we go k equal 2, you'll have xk, or x2 here, e to negative x1, negative x2. If we have k equal 3, we have x3, e to negative x1, negative x2, negative x3, and so on and so forth. So every term in this sum has an e to the negative x1, and what we know about, you know, exponents where you add or subtract the powers, we can actually factor one of them out. So you can factor out e to the negative x1, which leaves us with this sum. And this sum has n minus 1 terms. And by the inductive hypothesis, we know it's bounded above by 1. So this equality that we have here is bounded above by, write the same thing down here, x1 e to negative x1, plus we have e to negative x1 times 1, which I haven't written, but it's there. And we can factor out e to negative x1, write it this way, and again, using the same trick where we have the Taylor series expansion in the bottom, we can make the bottom smaller to make the fraction bigger. So we have 1 plus x1 over 1 plus x1, and that, of course, is equal to 1. Which means that for every single n that we have, our partial sum is going to be bounded above by 1. So if you define a sequence, an, to be essentially the partial sums, this sequence is always bounded above by 1 and 0. Not that we really need that, but since the right-hand side's upper bound is independent of n, we can just take the limit as n tends toward infinity, and we get something bounded above by 1. Anyway, boom, we have the proof. I think there's another way of doing it, which is much longer, but this way was pretty short. I believe that problem was verified by the instructor as well. There's something about the very end of it that doesn't, like, everything seems completely reasonable to me, but at the very end I get nervous, but I do believe the instructor approved it for us. We're allowed to check him. We're allowed to check our work with him. It's okay with him. He actually encourages us to do it. But anyway, the biggest problem that I have this weekend is that I need to prove these horrible long theorems. The first theorem, well, okay, so as you saw from my cartoon up here, the struggling grad student spits on that thing, and that thing being the Steinitz theorem. Steinitz's theorem took us 2 days to prove, and of the theorem list, he has actually split the proof of Steinitz into 4 questions, which means that on the test, when he gives us a theorem, it could be any one of these 6 questions here, but the first 4 questions come from the proof of Steinitz's theorem. And I should have the claim of Steinitz somewhere here, which is bad because I don't even know what Steinitz theorem says. I take horrible notes. Yeah. Here's what Steinitz says. Suppose that we have a sequence of vectors from Rd such that the sum of those vectors converge to something in Rd, some vector in Rd, which for some reason we call S. Consider all permutations pi from n to n such that the following series converges. So essentially we are rearranging the terms in the series. And we want to prove that the set of their possible sums, S plus V, where S is the vector that we have here, and V is a linear, any linear subspace. Okay, maybe not. V is any linear subspace of Rd, where V is equal to the orthogonal complement of W, where W is this thing. Apparently we want to show... Wait, what's the claim? Then the set of their possible... so the set of possible sums is of the form S plus V. Okay, so that's what Steinitz says. Yeah, like I said, this theorem took 2 days to prove. And it's split up into 4 pieces for us to prove. And I don't have all of it memorized. The ones that I have dots next to are the ones I'm kind of comfortable with, although I've really seen it once. The one that I'm most comfortable with is 3 of the first 4. V tilde is a linear subspace. Question 5 is the one of these 6. It's the one that I'm most comfortable with. But of Steinitz, I like the third one the most. V tilde is a linear subspace. I'm not going to go through all this, but I will like hold it up here and you can pause and read it if you're interested. Obviously, the notation is a bit, you need to know what the notation says, but this was a proof of it given in class. Someone asked for him to prove. Actually, the person that asked him to prove this during the review session said, hey, can you prove this theorem? And he goes, oh yeah, it's a short one. And we spent like 30 minutes proving it. It's like, this is short? I don't know. But theorem 3 is the one I'm most comfortable with. There's the definition of phi tilde, if you're interested. And it's the one that I've practiced the second most of all these theorems. Couldn't get it on 2 pages, had to go to the third. And then we have the Bernoulli polynomials. This is garbage. Where's the good one? I don't even know. Euler-Maclaurin summation test. Yeah, this one's the easiest one. If I get good RNG on test day, I'll get this one. I can do this one pretty well. This one's not too bad. Although I should probably go over it a little bit more. It allows you to get within some precision that you predetermine of. Like, let's say that you have a series and you want to, and you know it converges, and you want to get a good estimate for what the value of that limit is. The Euler-Maclaurin summation test says, okay, if you want to be within 10 to like negative 1,000 power of the true answer, you can use this test, or this, whatever you want to call it, this method, to get an approximation that is within your error that you've predetermined. So I think as far as applied math goes, this is probably something that applied mathematicians would be really interested in, because they're all about approximating. Anyway, I have my work cut out for me. I still need to review over the other theorems from the list, which, I got buried in papers here. Where is it? Here it is. The last theorem we did, which was like 2 days ago, was the Littlewood-Tauberian theorem, which talks about Cesaro summation and Abel-Poisson summation, which are different ways of trying to get a series to converge. And you can read the statement, what it says there. I thought it wasn't going to be too bad, and I didn't think it was too bad, but there was a student in the class that came up to me and thought it was like the worst proof. And I don't think she thought it was the worst proof, but she was intimidated by how long it takes to prove. So we definitely have our work cut out for us. Like, none of these theorems are short. Lemma from Steinitz theorem is long. Question 2 was supposed to be short, but it turned out to be long. V tilde as a linear subspace is okay for me. I don't mind it. Question 4 I haven't studied. Question 5 is by far the easiest one. And then question 6 is also kind of long. So they're all super fun. Anyway, still working on measure theory measure theory videos. I have an interesting video that's going to be posted in about a month, which I'm not going to talk about. It's going to be a surprise. But the struggling grad student experience continues, and I'll continue to make more videos. Hopefully post more often, because I've been pretty busy and I don't get to post as much as I do, but they'll keep coming.